A very good morning, dear students. Myself, Professor Satish Handi from the Department of Mathematics, KLS, VDIT, Alia. So, here we are discussing about the lesson number 2 of Module 1. In the previous session, we have studied about what is limit, continuity, and differentiability, which is the lecture 1 for this Module 1. Now, today's topic we are going to discuss about Cauchy-Riemann equation in Cartesian and polar form. Let's begin. So we should know what is analytic function. A complex valued function w is equals to f of z is said to be analytic at a point z is equals to z0 if f dash of z exists and it is unique and z0 and also in the neighborhood of z0. If f of z is said to be analytic in the region given region and D and also the analytic function is also called as a regular function. Now let's go for the Cauchy-Riemann equation in Cartesian form. The statement says that the necessary and sufficient condition for a complex valued function w is equals to f of z, which is nothing but u of xy plus I into v of xy, may be analytic at a point z is equals to x plus iy is that there exist four first order continuous partial derivatives. What are the derivatives? Dou u by dou x, dou u by dou y, dou u by dou x and dou u by dou y, and satisfy dou u by dou x must be equals to dou u by dou y and dou u by dou y is equals to minus of dou u by dou x. Now here to prove this, let's first assume that f of z is analytic at a point z is equals to x plus iy. Now by the definition of analytic function, derivative exists, that means f dash of z exists and it is unique. Therefore, as you know, f dash of z is equals to limit as delta z tends to 0 f of z plus delta z minus f of z upon delta z in Cartesian form. F of z is equals to u of xy plus I into v of xy, and delta z is the increment corresponding to the increment delta x and delta y in x and y. Therefore, f dash of z becomes f dash of z will be equals to limit as delta z tends to 0 u of x plus delta x comma y plus delta y plus I into v of x plus delta x plus comma y plus delta y minus in the next bracket u of xy plus I into v of xy upon delta z, which is equals to limit as delta z tends to 0 u of x plus delta x comma y plus delta y minus u of xy upon delta z plus I into limit as delta z tends to 0 v of x plus delta x minus y plus delta y minus v of xy upon delta z. Now as we know that z is equals to x plus iy and therefore delta z will be equals to delta x plus I into delta y. Now we know that delta z tends to 0, that means either delta x tends to 0 or delta y tends to 0. Now we can let's take first case delta y is equals to 0, then delta z becomes delta x and delta z, as delta z tends to 0, that means delta x tends to 0. So in the first case you can see that f dash of z will be equals to limit as delta x tends to 0 u of x plus delta x comma y minus u of xy upon delta x plus I into limit as delta x tends to 0 v of x plus delta x comma y minus v of xy upon delta x. Therefore, f dash of z is equals to dou u by dou x plus I into dou u by dou x, which is equation 1. Case 2, let delta x tends equals to 0, therefore delta z is equals to 0, that implies I into delta y is equals to 0 or delta y tends to 0. So as we can say that f dash of z is equals to limit as delta y tends to 0 u of x comma y plus delta y minus u of xy upon I delta y plus I into limit as delta y tends to 0 v of x comma y plus delta y minus v of xy upon I into delta y. That means f dash of z is equals to dou u by dou y minus I into dou u by dou y. Name this as equation 2. If we equate the real and imaginary part, then dou u by dou x will be equals to dou u by dou y and dou u by dou y is equals to minus of dou u by dou x. Here are the some consequences, that is if f of z is equals to u plus iv is analytic function, then u and v both satisfy Laplace equation. That means dou square u by dou x square plus dou square u by dou y square equals to 0. Similarly, dou square u by dou x square plus dou square u by dou y square equals to 0. The function, second one, the function satisfy Laplace equation is called as a harmonic function. If f of z is equals to u plus iv is an analytic function, then the equation uxy equals to c1 and vxy equals to c2 represents orthogonal family of curves. If f of z is analytic at a point z is equals to x comma y, then u and v satisfies your equation. But the converse is not true. Means if the function is analytic, then it will be satisfying CR equation. But if the CR equation is satisfied, that doesn't imply the condition for analyticness. Now, secondly, the theorem Cauchy-Riemann equation in polar form. Now, in this form, if z is equals to r into e raised to I theta, that is f of z is equals to f of r into e raised to I theta, which is equals to u r theta plus I into v r theta, is analytic at a point z, and then there exist four continuous first order partial derivatives dou u by dou r, dou u by dou theta, dou u by dou r, dou u by dou theta, and satisfy the equation dou u by dou r is equals to 1 by r into dou u by dou theta, and dou u by dou r is equals to minus 1 by r into dou u by dou theta. Now, proof for this on the similar line as we have proved, that is one proof, and there is one more proof. We can give it as alternate proof. Usually I try to give this particular proof if z is equals to r into e raised to I theta. The previous proof we can try to get this on the similar line what you have got in case of Cartesian form. That is, if alternately if you want to prove this, then if as a proof we can take if r comma theta are the polar coordinates of a point whose Cartesian coordinates are x comma y, then z is equals to x plus iy equals to r into e raised to I theta. Therefore, f of z is equals to u plus iv f of r into e raised to I theta. And name this as equation 1. Differentiating 1 partially with respect to r and theta, ur plus I into vr will be equals to f dash of r into e raised to I theta into e raised to I theta. So, that is u theta plus, and similarly u theta plus I theta, I into v theta will be equals to f dash of r into e raised to I theta into I into r into e raised to I theta, which is nothing but by the previous equation we can write it as I r into bracket ur plus I into vr. That means ur will be equals to 1 by r into v theta, and vr is equals to minus 1 by r into u theta. So, this is the proof for the CR equation in polar form. To summarize the topic, at the end of the session, students will understand how to derive the expression for or the Cauchy-Riemann equation in Cartesian and polar form. And here I will be giving here with the additional reference through YouTube channels. I request each and every one of you to go through these channels. So with this, I conclude today's session. Thank you.